we developed Project 22100, spent grain reuse and dealcoholizing process. I'm Brennan Breen. Also on the team is Marco Garcia, Ian Alexander, and Sean Alexander. And just some very brief background on our team. At the start of the semester, our original design mentor was terminated and we had to scrap our project. So everything that you'll see is the result of one semester of work. With our new design, our team was tasked with finding potential uses for regeneratively farmed grains from Open Flats Ranch. By finding uses for this grain, our design seeks to promote sustainable land and water management agriculture, as well as a broader regenerative economy. And we landed on two projects that could incorporate this grain. First was to design a de-alcoholizing process to convert beer into non-alcoholic beer. Marco and Sean worked on this project. And second was to design a process using brewers' spent grain, the primary waste stream from brewing, to generate a new product. And Ian and I were tasked with working on this.
The first problem that we looked at is Open Flats Ranch needs to find a profitable use for their new barley product. We decided our project should be using Open Flats' new barley to produce a non-alcoholic beer into some breweries. This gave us our objective statement for the project, which is to design a process that produces high-quality, non-alcoholic beer while minimizing its carbon footprint and reusing all the waste streams. After weighing various criteria and constraints for our project, we found that using vacuum distillation with sieve trays was the best method. Distillation columns are large towers with many trays inside. They are able to separate two liquids to a certain extent using the schematic shown here. When beer is fed to the column at a certain temperature and pressure, it will start to circulate through it. Beer can be thought of as mainly a mixture of ethanol and water. Ethanol boils at a lower temperature than water, so at the right conditions, there will be mainly ethanol vaporizing and traveling up the column, while the water condenses and travels down the column. The schematic shows the ethanol vapor rising and bubbling through the liquid coming down. Bubbling the vapor through the liquid allows the mixture to reach the right extent of separation. We chose to have this process operate under vacuum pressure because that allows the column temperature to be lower, and a lower column temperature leads to less breakdown of the flavor molecules inside the beer, which gives a better tasting beer in the end. Our final distillation process includes much more than just the column. Starting at the bottom left of this diagram, freshly made beer starts in a tank under standard conditions and is then pumped into the distillation column. Before it reaches the column, it passes through a heat exchanger to bring it up from room temperature to the column operating temperature. From there, the separation in the column occurs, and we're left with two streams, non-alcoholic beer and an extremely concentrated ethanol. The concentrated ethanol exits the top of the column as a vapor and then is completely condensed into a holding tank. A reflux timer then sends a portion of that ethanol back into the column to continue the mass transfer process. The rest of the ethanol is then sent to another holding tank before it's collected and sold. The non-alcoholic beer exits the bottom of the column where it's partially vaporized. The vapor returns to the column again to continue the mass transfer process. The liquid portion, which is still warm at this point, is pumped through a heat exchanger to cool off before being collected in its final holding tank. A very small amount of fresh beer is then mixed with the non-alcoholic beer to restore any flavor loss that might have happened throughout the process.
The table to the right presents the purchase cost of all the equipment associated with the process. The largest purchase cost associated with the process is a stainless steel distillation column at $66,292. The smallest purchase cost associated with the process is the peristaltic pumps, which are $1,240. The cost of the equipment totals out to be $116,549. The table to the right presents the annual cost and revenue made from the process. The denatured ethanol produced from the back-end distillation column gets a total revenue of $5,961. To break even with the total annual cost, which is $61,801, non-alcoholic beer must be sold at $1.24 per can. The $1.50 and $2.10 price points are competitive with other non-alcoholic beer brands. The cost associated with the employee is 1/5 of their total salary plus benefits due to the process operating only once a week. The total production of non-alcoholic beer and denatured ethanol for our process per year is 45,173 11-ounce cans, 179 gallons of ethanol. The graph to the right represents how long the process will take to overcome the initial investment, assuming it will be operational after 2 years. The black line shows that selling non-alcoholic beer at 99 cents will never generate profit for the process. The gray line shows that selling non-alcoholic beer at $1.50 will take longer than 20 years to pay off the process. The yellow line shows that selling non-alcoholic beer at $2.10 would take less than 9 years to pay off the process. Further recommendations for the project include changing the distillation column into a still for the process, since a still may be more cost effective. Another recommendation includes using solar thermal heating for the reboiler to reduce utilities and a way to implement renewable energy for the process.
The second project is focused on spent grain reuse. Some background. Beer is the most popular low alcohol beverage in the world. However, the brewing process generates large volumes of waste. About 85% of the total waste is brewer spent grains, also known as BSG. Typically, BSG is a waste product that is thrown away or used as an animal feed additive for its high sugar and amino acid content, but has the potential to be upcycled into more valuable commodities. The objective of our project is to utilize brewer spent grains from local Tucson breweries using Oman's flats grains to create high quality consumer products and promote a local circular economy.
So here's our proposed production scheme for the mushroom substrate. Conventionally, mushroom growing substrate is made from a 50-50 mix of a nitrogen-rich material and carbon-rich materials. So our nitrogen-rich material is going to be brewer spent grain, which will be generated from breweries using specialty grain sourced from Open Flats Ranch. BSG also usually has a moisture content around 80%, so it should provide enough water to hydrate our entire substrate mixture. And for our carbon-rich materials, we'll be using a mixture of salt cedar and wheat straw, also from Oatman Flats Ranch. And salt cedar is an invasive species along the Gila River Wash. It's all that vegetation you can see behind the right line in that image in the top right corner of the screen. So by removing the salt cedar, our project can also be part of a broader plan to help revegetate some of the native flora along that section of the wash. And both the salt cedar and the wheat straw will be processed on site with a shredder to reduce their particle size. And after mixing the substrate, we'll be packaging it to 8-pound substrate grow blocks. And then these 8-pound blocks will be sterilized in a 150-gallon atmospheric steam sterilizer to ensure that any competing microorganisms are denatured.
In the economic analysis of this project, a basis of 400 pounds of BSG was processed every week. This is reflective of BSG waste from a small brewery. The total capital investment of this project is a little over 27 grand, and the annual net earnings reach about 7 grand. The project will take around 3.25 years to recover their original investment. The local edible mushroom market is a lucrative industry with a high potential economic upside. However, potential economic hazards still exist for the proposed project. The proposed project will have to directly compete against established local mushroom companies such as Desert Pearl Mushrooms and Southwest Mushrooms. Also, due to time constraint, the efficacy of using BSG, salt cedar, and specialty wheat straw in a mushroom substrate has not been proven. These mushroom substrate components will need to actively compete against the industry's traditional masters mix. Next steps and improvements that we would propose for this project include material characterization and a test run of the proposed process. A macronutrient test should be conducted on each of the substrate materials to identify the total carbon and nitrogen components. This way, the substrate materials can be manipulated to more closely emulate the carbon and nitrogen ratio found in traditional masters mix. A test run of the proposed process should be conducted to identify areas of improvement. Contamination can occur during the handling process and should be minimized once identified. Contamination of the blocks will reduce the profitability of the project. Once the substrate block has been reduced, mushroom growth experiments should be conducted to identify the biological effectiveness of the substrate materials compared to traditional masters mix.